So, yes, slope fields, you've dealt with them a little bit. It's literally a graph of a bunch of partial line segments indicating what the slope at that particular point is, right? And the thing that's important about slope fields is they represent graphically the solution curve for a differential equation. So on 7.1, we've talked about differential equations in the past, but what's important to understand is what you're looking at when you look at a slope field. You are looking at all the possible different solution curves for a particular differential equation. And what's important also to understand is there is more than one possible solution curve, because we can have vertical shifts and horizontal shifts. Our C value can kind of impact the placement of that solution curve. And then I just, you don't have to put these in your notes, but I just went and Googled a bunch of solution curves, and the thing, or slope fields. The thing that the analogy that I like to use, that I read somewhere, heard somewhere, that I think is a good analogy, and especially down here, since we have waters around us in many places, whether they're canals or rivers or the Gulf or oceans, whatever. The way that it was described is if you took a hat and placed it on top of the water, the current would take the hat in a specific direction, right? And you guys have spent more time out on the water than probably I have, but when you've killed the engine on your boat and your boat just wants to drift and the current pulls you, it's the same idea. So if you set the hat in the water in a certain place, this one obviously would take it in a circular motion. This one wants to funnel in and kind of go toward this line here. And then these, depending on which side you put it on, we have this little gap in between here, and we have a little gap here, and I'm going to talk about those gaps here. So there's that flow, if you will, of in general of a slope field. Now, we're going to start off super easy, and I'm going to blow through this pretty quickly, okay? You definitely want to have your book open, and because I'm going to use I think we're going to go through about 4 or 5 examples. So page 161 is where you want to be. And this differential equation we're going to use over and over again for the purposes of our example, okay? So yeah, this is a differential equation because I have a derivative in the equation, and it's telling me that dy dx is negative x over y. And so it's asking for you to find the slope at any given point. Well, that's simple enough, right? Plug the value in, and you'll get the slope, because dy dx, of course, in calculus, we know that as the slope instead of m, and we'll talk about m later anyway. So plug 3 in for x, 2 in for y, and so the slope at the point 3, 2 is negative 3 over 2. So if you were to construct a slope field, you'd have something a little bit steeper than negative 1, okay? So go ahead and find the slope for these final 3. And then we'll talk about this question, why you can't have slope at y equals 0. Okay. So, of course, when I plug negative 1 in for x, that becomes positive. Y is 3, so that's 1/3. This is 2 over negative 1, and this is negative 2 over negative 2. So these are the slopes that you should have gotten, okay? The question is, why can't you find slopes at y equals 0? So why can't you find slopes when y equals 0? Can't be in the denominator. This would be undefined. So there will be no slope. There'll be no little tick mark whenever y equals 0, okay? There's no slope there, y equals 0, because derivative is undefined. So one of the things that we look for in slope fields is a couple of these things. Find out where there's no slopes, where there's no little tick marks, those little line segments, or also find where there are horizontal line segments, because that indicates that we have a slope of 0. So those are sort of key things to look for as you work through these, okay? Here's what's really important. There's lots of different solutions, okay? Differential equations in general, have many possible solutions because the slopes are changing. As we move from point to point throughout the field, the slope changes. And so we can have different solution curves in different places, and they're all still valid, okay? We talk about sometimes when we were doing, which chapter was it? When we were doing curve sketching, sometimes we're like, oh, this is one possible solution, but if there was a vertical shift, this would also be a possible curve for this particular equation. There's a similar thing going on with slope fields and solutions to differential equations. There are many possible solutions because it just depends on which particular spot on the field you're looking at. That being said, whatever the solution is, if I compare them to the other solutions, are going to have something very much in common. They're going to have similar shape. The direction might be off a little bit, but that's something to kind of keep in mind. Again, theory. All right, this is example 2. So either take a picture of this or take a picture from your book. But if you notice here, this is a partial slope field. And obviously, the thing that bothers me a little bit about this is we know that a point is a spot. It doesn't have the kind of area that it's indicating here, but it's more for the purposes of trying to get you to understand where it should be. Now, this is the same equation. So if you notice here, when y equals 0, there are no points. So there's a little gap between the top slope field and the bottom slope field. It's obviously all one slope field, okay? Now, what we're going to do first is just specifically look at one particular point, okay? We're going to look at this point here. And then we're going to draw the little line segment that goes with that. So what are the coordinates of that point? 2, -2. And I think we already did that one, didn't we? Wasn't that on the previous? Okay, so what is the slope at 2, -2? It's 1, okay? So what we're going to do, so when we have something of slope 1, what kind of angle are we kind of talking about? A 45, okay? So what I need to do is draw one of these as a 45, okay? And it's a positive 45 since x is 1. Or sorry, the slope is 1. And so what that would look like is just something like that. It doesn't have to be perfect. What's going to happen is what you'll see, particularly in this problem. So see how this one is tilted even further down. This one's kind of up, and so this one's going to go further up. There's always a little pattern if you go kind of up and down, and you can kind of see how that's going to happen. So what I would like you to do now is try to quickly go through and complete the slope field for all the points that don't have a little line segment on them, okay? Again, once you start figuring 1 or 2 of them out, you'll see these patterns that happen. Obviously, notice here, actually, let's look here. Let's look at quadrant 2 and quadrant 3. See how the tilt of each of the given line segments is the same, except it's just going in the opposite direction because of that reflection. But the angle is the same. It's just the one is negative, one is positive. And you can use that to kind of fill that out. So go ahead and do that real quick. You certainly can look at each coordinate too. That's where I would start. I'd be looking at some of the coordinates and trying to figure out how that's going to work. And then when you get done, you can just kind of look at the screen and compare to mine. So hopefully you noticed that you kind of, as you sort of worked closer to the y-axis, the line segments got steeper, and as you get further away, they tend to get flatter, okay? Same thing happening up here. As you work up away from this line, they're steep, and they get flatter as you work your way up. Now the angle, of course, is opposite, and we have this circular looking slope field with a big exception, okay? There are no circles here. Why not? And what is it instead of circles? Semicircles. Why do you say that? Because there's a big hole. There's a big gap right in the middle. We can't connect these this way. So you're going to have a semicircle here. You're going to have a semicircle there. Okay? Now, we're going to move right into example 3. And you can probably take a picture of this if you want. You can screenshot it from Brooke, whichever. But there's 3 things that I've highlighted here. Okay? So, example 2, we made the slope field. Now, in blue, part of the thing that we're trying to do is say starting at the point 0, 1. Okay, 0, 1. That's this point right here. Follow the flow of the slopes to sketch a solution curve containing 0, 1. Well, since this is kind of a semicircle, how do I make it sort of end here at the x-axis? What do I do? Open circles. Very good. Okay. And it says your graph should be parallel. Let's see why they put that in parentheses, right? Because as you work your way down, it's sort of flat here, and then it's kind of runs parallel. It doesn't run to this point, because then it would be a straight line. But it starts curving, because the slope is ever changing throughout the whole thing. So it's going to be kind of inside here somewhere, and it'd be parallel to these particular marks, and those are the only ones we have from this point, okay? What's also important is that, well, I'll get to this in a sec. So try and sketch that one from 0, 1, and then take a look at how you think it went. So it definitely has to go through the point 0, 1. If you sort of spaced it out a little further here, that would be okay. But again, it doesn't have to be perfect. We're just trying to get an idea. All right. The key thing here is the solution curve must represent a function. We'll talk about that in a minute. All right, do that one through -1, 1. So here's -1, 1. So now draw a solution curve through this point. And if you really want to get crazy, you can do the last one too through 0, -3, which is down here. So here's the one through -1, 1. Should look like that, or close to that. Okay. And then the one through 0, -3 is going to be down here. So now it's going to look something like this. Okay. Again, doesn't have to be. It could be, yours could be off a little bit by mine. That's okay. We're just trying to get the idea. Now, the question they ask us is, what type of graph does this differential function seem to be producing? We talked about before, it seems like a circle, but because of the fact that we have this hole right here, it have to be semicircles. What's really important, this is the real important part of this, it has to be a function. And so if you go back to your algebra days, and we did the vertical line test, right? And we had to make sure no vertical line ever hit the graph more than once. If it was an actual circle, it's not a function. A circle is not a function. Remember that a solution to a differential equation is y equals something. Right? So when that y equals is in there, we can't have a y squared. In order to get a circle, we'd have to have a y squared in our solution equation, which we're not allowed to have, okay? So let's keep moving. Questions before we do? You guys have drawn slope fields before and drawn solution curves before, yes?
How do you know if it's like downwards or above, like lower above the x-axis?
Well, it's these, all 3 of these curves are based off of the point that they gave us, right? And both of these points had y's that were 1, so they were above the x-axis. And knowing that there's this hole right here in the middle, since I have to start up here, you can't cross over it. And this one was down in the bottom, down here. So I knew I couldn't cross over it going upward. So it's based off the point they give you. The one thing that I think is important is what we have here are 3 potential solution curves. So it lends itself to that idea that there could be multiple solution curves for one equation. It depends on what point we're looking at. And again, that has a lot to do with the C value, because these could all be initial conditions to help us determine what C is. So for the solution for this, and the thing that's interesting about slope fields, and also with what we're going to do tomorrow, is a lot of this stuff exists for differential equations that are not separable. The differential equations that we've looked at so far in our life that we can deal with are separable. This one is also separable. But when we get into more complicated calculus, we will have differential equations that are not separable, and so we need other strategies to help come up with those solutions. This is one of them, okay? And of course, we use something that we can relate to, that we can make work for us to help us understand the concept. Second, we want to find the equation for this graph, because this is 0, 1. So if we find the equation for this graph, then we're good to go. That's what we're doing. All right, same equation again. Now we're at example 4. So we're going through these, okay? It says find the particular solution in the form y equals f of x, meaning y equals. Okay, I need y equals to be my actual solution, whose graph goes through the point 0, 1. Right? In other words, I'm going to go back to this point, since they gave us the same point. Now, here's how this is going to work. Okay, again, this is just a note. Remember that solutions to differential equations are functions. This is why this is important. When we get to my final answer, it needs to be y equals. And as we go through this problem, and we've been talking about circles and semicircles, you'll see what I mean and why that's important. Okay, and then actually, Jackson, this is going to get to your question about how do you know if it's the top half or the bottom half. And it all has to do with the point that they gave us. So in this particular problem, it's telling us to solve the differential equations. That means this is separable. So I get to get the y and the dy together, the x and the dx together. Okay, and in this case, it's pretty simple. So why don't you go ahead and do that? Go ahead and solve the actual differential equation. But I want you to get it down to where you just get rid of where you've just integrated. Don't actually try to find C yet. Just integrate the first time, and then we'll kind of go from there. And then after you're done with that, you can look and see and compare yours to mine. And then I'll go through it, and we'll talk about some of the important pieces to this type of situation. And I'm pretty sure I did something that you didn't do. And I want to talk about why I did that here in a second, but I'll give you a sec. I'll give you a minute to do that. All right, let's talk about the algebra from this step to this step, where I got rid of the fractions. And I changed this from C1 to C2, okay? Could you have left it like this? Sure. But one of the things that's nice about the general form after you integrate is C is just some constant. It doesn't matter what constant it is, it's just a constant. And of course, we would love a world where there weren't crappy fractions every once in a while. So if I just multiply through by 2, in reality, what I would get over here is y squared equals negative x squared plus 2 times C1. Well, this is just another way of saying a constant. We don't need to be all that concerned about what the constant is. We just know that it's another constant. And of course, this equation is much cleaner than this equation, okay? So that's why I did that, and you're allowed to do that. And to be honest with you, you should be getting to a place intellectually where you can understand how this is no different than this, and that this is nicer and cleaner and better, okay? Now, here's what's really important, okay? And this is where we get into this situation, because we talked about this the other day. I think it was in 7.1. in order to solve for y, I have to square root both sides, and you have to take the plus or minus. Well, we can't have two parts. There can't be a plus. It's either the positive or the negative. And here's where you have to understand what the given point is. All right? They gave us a point where y was already positive, which means when I go to square root this, I don't need to worry about the negative square root because y is not negative. Y is positive. And so in this case, when I take the square root, all we have to worry about is the positive one based off the point they gave us. Now, on that previous example 3, we looked at 3 points. And so when we go through example 5, you'll see what I mean here in a second, okay? Now, the only thing I need to do here is find C2, right? And that's where I'm going to use this point to do that. Plug 0 in for x, 1 for y, and simple enough, C2 equals 1. And so my final solution for this particular solution to this differential equation that goes through this point ends up being this, okay? Again, a semicircle, right? A semicircle is always the square root of this. This is really x squared plus y squared equals c. And we know that's a circle. But when we square root it, we only get half it. And for those of you who have the TI 84s, you know that in order to graph a circle on your calculator, you have to enter 2 semicircles anyway. So that kind of lends itself to that, okay? All right, we're going to keep moving because I just want to, and I'm going to show you this quickly. If you want to wait to the end to take a picture, you can. But my purpose of going through this example is simply to say, look, here's this point that we talked about before. The y is negative now. The steps are all exactly the same, except when I go find c, okay, I'm going to plug in. And also, instead of using the positive square root, I'm going to use the negative square root because they've told us from the beginning that y is negative, okay? That's really the main difference between these last 2 examples. Okay, because there was part A, part B. So part B, same idea. You did the same work, except now we're going to take the negative square root because the y is negative in our problem. And so then when I find C, I plug everything in the same way. C2 is 9. And then this is the particular solution of the green. I guess I should have made it green, right? Our green semicircle that we drew, that would be the equation for it. Right? And notice, foundationally, we start in the same place other than this minus. Okay, that's the biggest contrast I want to make between those 2 kinds of problems. How do you know if you use the positive or the negative? Well, it depends on what you've been given. Okay, and in this case, they gave us a y was negative. All right, we have 2 more examples to get through, and I think we're going to be good. Okay. Any questions before we go to those examples? First thing, here's example 6. It's a multiple choice. This is a typical kind of thing you might see on the multiple choice section of the exam. All right. It says, which of the differential equations below matches the slope field at the right? Now, remember something as we look at this. This represents the solution to the differential equation. And what's important is it is asking me for the equation. It is not asking me for a graph of, or an equation of the solution. It's not asking me for a graph of the solution. It's asking which equation would produce this as a solution. Now, in order to do problems like this, you've got to have a sense of what kind of thing we're looking at. And if we look at this flow on this slope field, what kind of shape does it look like? Yeah, cubic. Cubic's the word you're looking for. So I just put this in there, right? It kind of looks like it's going like that. That should validate our idea of a cubic, okay? I just followed some of these points right in here. I just followed those. Yeah. Again, this, to be honest, this sketch is not important other than to validate the idea that it's cubic-y. I mean, if you would have gone this way and made it flatter and wider, it's fine. It just validates the idea that the solution is a cubic. Well, think about what a differential equation is, right? It's always the derivative. Well, what is the derivative of a cubic?
3x squared.
Right, it's a quadratic. So here's where it's going. First off, the solution appears to be some type of a cubic. Important. Okay, when I take the derivative of that, I end up with a quadratic, which means, yeah, an x squared. Okay, so right off the bat, we know that we can eliminate anything that's not a quadratic. Now, it's probably better to say degree 2. You know what? Actually, I don't want to even say that because that infers that it's a polynomial. I'm going to say it's going to have, there's going to be a second power. No, I'm not going to say that. I don't like that either. Here we go. Power of 2, final answer. There's going to be a power of 2 in my answer, okay, in my actual differential equation. So the question becomes, which one is it? This one has a y squared in it. This one has an x squared in it. Here's where we boil this one down and make it kind of easier. We have a dilemma right here. What is the slope of all of those? 1. So which one do you think it is? Is it D or E? So you can pick a point, right, if you wanted to. What are all do the x values stay the same here? No, the x values are changing. So if the x values are changing, then there's no way that the slope stays 1. Are the y values changing? No. So there's my 0 and my y prime, dy dx, slope is 1. So yes, that's how we work to find the actual differential equation that goes with this slope field. So we kind of work it backwards. We have to have a little bit of an understanding of what happens when you take the derivative of the curve and what kind of thing will you get. Again, quadratic's probably not the best way to put it because quadratics have very specific, when you take a parabola and turn it 90 degrees, it's no longer a quadratic. So this is bad, but hopefully you get the idea. Again, power of 2 is better. Let's look at one more example, okay? In this example, this is example 7. Now it's actually asking for which one of these could be the solution curves equation. Okay, the last problem was not asking us for the solution curves equation, it was looking for the differential equation. This one is saying, okay, which of these could be the solution to the curve that you draw? Now, I drew this curve. Again, you can draw whatever curve in a different place than me if you wanted to, but we can see that it kind of moves like that, okay? And so this requires, of course, you to have some level of understanding of what all these different graphs look like. Of course, these three are much related, right? What does this kind of look like? What curve does it sort of look like? Do you remember what either of these graphs, do you remember what this graph looks like or what this graph looks like?
The natural log of x will be negative.
Correct. How about this one? What does this one look like? Like a J. All right, so let's think about this. All right, this one kind of looks like this. Exponential growth, right? We've talked about that. What does this one look like?
It's like I'll describe it, but like a little hump.
Yeah, that one kind of goes like that, right? I think, doesn't it?
Yeah.
All right, so let's throw that one out. Let's throw this one out. What is this negative in front of this going to do to it?
Flip it on the y-axis.
Over the y-axis or over the x-axis?
Oh, x-axis. I was thinking of it vertically.
Okay, so is this gonna work? Does this one work for that? No, it doesn't. All right. So right off the bat, we can throw a bunch of them out. Okay, and so the same thing here. If I take this and I flip it over the x-axis, it's gonna look like this, right? It's gonna be down here. So we can throw those out. We can throw those two out. This is basically flip that. That's this one. This is flip it over the y-axis. And I flip this over the y-axis. This is what I end up with. Okay. So that is my final answer.
That's decay, right?
That is decay, actually. You're right. That's a decay type of problem, right? And if you think about it, the y values are going down as the x values are increasing. That is decay, and we talked about that in 7.1. All right.